Okay, so here we are, lecture two. I decided my background today would be in the center of Paris. I was in Paris more than 20 years ago. Uh, anyway, we finished the material on area between curves, which was section 6.1, and I am going to cover 6.2 today, which is about volume of solids. Uh, Solids that are particularly easy to describe in terms of functions. So let me get started. I'm going to share the screen. I'm going to share my whiteboard. Okay, so let's get started. So this is, as I said, section 6.2, which is about computing volume in terms of integration. And the basic idea is this. Suppose I'm going to put some axes in for now. You'll see why in a moment. Here's the x-axis. Here's the y-axis. And we have a solid. Maybe it looks like this. Here's my solid. And it's defined between x equals a and x equals b. And so over every point between a and b, we have a cross-section. Think of taking a blade out, a sword, and slicing the solid at x. Okay, so there is a cross-section generated by that. So we have so let a of x be the area of the cross-section at x. And now what I'm going to do is I'm going to take a little slab. In fact, the method we're going to introduce is called the slab method. So we have a slab, and that slab, what I'm going to try to do is estimate the volume of the slab. So the slab will have width delta x, let's say. Okay, so I'm going to draw a bigger picture of the slab. Now, the slab is not a perfect cylinder, but it's approximately a cylinder, so long as delta x is very small, delta x being the width. And if we pretend it's a cylinder, then you have a radius whose height is, if this point is called xi, let's say, because it's some test point. So the radius is f of xi, and the thickness is delta x. And the volume of such a slab is approximately the volume of a standard cylinder. So the volume of the slab is approximately equal to, well, it's the area of the cross section. Well, let me retract that. Let me go back. So suppose we just, let me erase this. We don't have a function here. Okay, so we have the area at x. So that's given by the area of, if this is xi, it's the area, we're going to take the area a of xi. So let's do that. So the volume of the slab is the area of the side times the thickness. So it's a of xi times delta x. Okay. So that's for each slab, and what we do in calculus was we chop up the interval AB into a lot of subintervals, x0, x1, x0 is A, x1, x2, etc., all the way up to xn. And for each x1, x2, although you get a slab. And then we're going to sum up the slabs. So the volume of the solid is approximately given by, it's not exactly given by, a Riemann sum. I goes from 1 to n, say, of A of xi times delta x. So now what we do is we increase the number of points in this subdivision, which means we're going to take n going to infinity, and that becomes a limit. And so the volume of the solid in the limit, the limit of this Riemann sum becomes an integral. It's the integral from a to b of a of x dx. So that's the basic volume formula in section 6.2 that we're going to use. Now, let's start off with a very common example. It's a standard example. You all learned in high school what the volume of a sphere of radius r is. So let us do a calculation of the volume of the sphere using this method. You never learned probably how to make that computation. You're going to see now where that computation comes from. So suppose we take a sphere of radius r. So the way I'm going to understand that is I'm going to take, oops, that's really bad, very bad handwriting, bad drawing. So we take the coordinate plane and we put a, let's say a semicircle. So that's y equals the square root of r squared minus x squared. And we rotate it around the x-axis. So I'm going to do a solid of rotation, that's called. And when we rotate, we get a sphere of radius r. So this is called a solid of rotation of a curve. And so what we have to do is compute the cross-sectional area of each cross-section. So let's draw the cross-section again. So if that's the point x, then what's the area of this cross section? Well, it's an area of a circle. And what is the radius of that circle? The radius is the height, which is the square root of r squared minus x squared. So a of x in this case is given by, it's given by pi times the radius squared, which is the square root of r squared minus x squared, quantity squared, which is pi r squared minus x squared. Oops. So what is the volume? The volume, I'll call it V, is the integral. Now we're integrating from minus, x is going from minus r to r here. So minus r to r of pi times r squared minus x squared. R here is a constant, of course, dx. Okay, so that is the correct setup, but we can actually simplify our life by using symmetry. You see, the volume of the right hemisphere and the volume of the left hemisphere turn out to be the same. So this is going to be twice the integral from 0 to r. This saves us some arithmetic. That's why I'm doing it. R squared minus x squared dx. Of course, you don't need to do this, but I'm saving myself some effort here by doing it. So you get 2 pi when we integrate, and then we have to integrate r squared minus x squared. So that's r squared x minus x cubed over 3. And x is going from 0 to r, so you're going to get 2 pi. Evaluation at r gives r cubed minus r cubed over 3. And the evaluation at 0 gives nothing. And if you simplify, you get 4/3 pi r cubed, which is the well-known formula. And that's the correct formula for the volume of a sphere. Okay, so I think for the rest of this lecture, I'm just going to do some problems from the exercises. This is a problem-centered course, as you probably know. Okay, so let me erase the whiteboard. And the problem I'm going to do now is in section 6.2, and it's exercise 4. So 6.2 exercise 4. So what does that say? So if you read the problem, we're supposed to find the volume of a solid given by rotating a certain region around the x-axis. So the region in question is bounded by y equals e to the x, the exponential function, y equals 0, and x equals -1, and x equals 1. We have to look at that region, and we rotate it around the x-axis to get a solid of revolution. So let's draw the picture. So y equals e to the x is this function here, and we're interested for x being between -1 and 1, and y should be bigger than 0, so it's this region that we're rotating. And when we rotate it, I'll draw the rough picture of what it looks like when it's rotated. It looks like this kind of horn shape, this solid here. I'm not going to fill it in. Okay, so the important thing is to figure out what cross sections look like. So if this is x, what is a cross, when we rotate it around, what is the, what happens is you're going to get a circle that's generated by this. And what is the area of the circle at x, at this circle? Here, the circle is given by rotating around. So, and what is the height of the circle? The radius of the circle is e to the x. That's the radius. So a of x, therefore, is pi times the radius squared. So pi times e to the x quantity squared, or pi e to the 2x. Okay, so the volume is therefore given by the integral. Now x is going from -1 to 1. So -1 to 1, pi times e to the 2x dx. And so we have to find the antiderivative of e to the 2x, and you can sort of figure out that it should be e to the 2x again, but there's a fudge factor of 1/2, because when you differentiate e to the 2x, you get 2e to the 2x. We have to cancel that 2. And we have to evaluate from -1 to 1, and this is going to give us pi over 2 times e squared times e to the -2. And that is the answer to this problem, I hope. Okay, so that's 6.2 example exercise 4. Let's do 6.2 exercise 5 next. Let me clear the board. So 6.2 exercise 5. So how does that work? So the curve in this case, the region is given by the curve x equals twice the square root of y, x equals 0, y equals 9. This is the region in question, and we have to now rotate it not around the x-axis, but about the y-axis. So it's a different sort of problem. Okay, so one way to sort of understand what the graph of this looks like, by the way, is solve for, you could think of this as y equals x squared over 4. It's that curve, right? So, and that's a parabola. So what you're doing is you're taking a parabola and it goes through the origin. It looks like y equals x squared a bit. And up to y equals 9. So this point here, if y is 9, x is 6. So it's 6, 9, this point here. And you're going to be rotating this shape around the y-axis, and that generates something called a paraboloid. It turns out it has a name, paraboloid. It's parabolic. Okay, good. So so now we have to, the slabs in this case, the cross sections should be taken along the y-axis because that's how it's set up. And here y is going from 0 to 9. Okay, so we have to figure out what if y is a point between 0 and 9, we have to figure out what a of y is actually equal to. A of y is, well, at the point y, what is this radius? The radius is given by twice the square root of y, right? Because that's the x value, that's the radius. So you're going to get pi times the radius squared. So pi times 2 times the square root of y, quantity squared. So that's 4 pi y. So the volume, v, is the integral from 0 to 9, because y is going from 0 to 9, of 4 pi y dy. And the rest of it is quite easy. The antiderivative of 4 pi y is 2 pi y squared from 0 to 9. And we get, if we plug in y equals 9, we get 162 times pi, and that's the answer. So that's cool. Okay, so I'm going to do another problem now, which is 6.2. This is a somewhat more difficult problem, exercise number 11. So let me clear the screen. Okay, so what is this problem? Oops. Exercise number 11. So in this case, you have the region y equals x squared, bounded by x equals y squared, and bounded by, so these two curves, which, by the way, x equals y squared in the first quadrant at least is y equals the square root of x. And now the rotation is not about a standard axis, it's about the line y equals 1. And that's what makes it more complicated. So here's the picture. So y equals 1 is over here. So I'll put a dotted line here. Okay, so y equals x squared is the parabola, and y equals square root of x. Well, it's x equals y squared is also a parabola. They meet at the point 1, 1 and at the origin. So the region that we're rotating around is this shape here. So we have to figure out when we rotate it around to generate a solid, what a cross section looks like. So let's take a point X, and we rotate it around. What happens is, think of like a flywheel or something. This is going to be rotated around a spindle, an axis, and what you get is it's going to be given by. Well, I'm not going to give the side. I'm going to give the not the view we see. I'm going to give the side view. So let me erase this picture and draw it on the side. So what does it look like? It looks like this. So it's going to look like this. It's going to be an annulus. Okay, and we have to figure, what is the area of an annulus? Well, if the annulus has a little radius and a big radius, capital R, so the area of the annulus is pi times big R squared minus pi times little r squared. So we have to figure out what r and little r is. So now we're at the point x. So a of x, okay, so now what do we got? So the big radius is the distance from the point on the parabola y equals x squared to the distance to y equals 1. So that distance you can see what it is. It's going to be pi. Okay, so what is that r? Well, let me write down what r is. In this case, r is going to be 1 minus x squared, right? It's the difference from 1 to x squared. And the little radius is the distance from the square root of x. Here's the square root of x. Y equals the square root of x. To so we're going to take the 1 minus the square root of x squared. Did I say that right? No, that's not right. I believe I wrote that wrong. Let me correct myself. It's 1 minus the square root of x itself, right? So let me correct that. It's the square root of x. So we're going to get pi times 1 minus x squared quantity squared minus pi times 1 minus the square root of x quantity squared. And so let me simplify this. This is pi. I'll factor out the pi. So we use the binomial formula. 1 minus 2x squared plus x to the fourth minus, well, it becomes, I'll put it in parentheses, 1 minus twice the square root of x. Oops, erase again. Plus x. So if this is arithmetic is correct, the algebra is correct, you should get pi times twice the square root of x minus x minus twice x squared, and then there should be plus x to the fourth. And that is indeed correct. Okay, so now we have the area of a cross section. The cross section is an annulus, I said, right? So the volume is going to be given, well, we're integrating over x, so there's a dx here. And x is going from 0 to 1 in the picture. And it's pi times this expression twice square root of x minus twice x squared plus x to the fourth dx. Okay, so now we can now just integrate this. So I'll bring the pi out. Okay, so the antiderivative of x to the 1/2 power, that's the square root of x, is 2/3 x to the 3/2. So we have to multiply that by 2 because there's a constant there. So it's 4/3 x to the 3/2 minus x squared over 2. That's the antiderivative of x minus 2/3 x cubed plus x to the 5th over 5. And we are evaluating from 0 to 1. Now the evaluation at 0 doesn't do anything here, but the evaluation at 1 does. So we're going to get pi times 4/3 minus 1/2 minus 2/3 plus 1/5. And we can combine all of these fractions into a single fraction with a common denominator, I guess, of 30. And what do you get? So you're going to get 40/30 minus 15/30 minus 20/30 plus 6/30. And that turns out to give you 11 pi over 30, and that's the answer to this problem. So this was a harder problem. I agree, but it illustrates that we can actually do fairly complicated problems with this. Okay, so I'm going to do one more problem today, and we will call it quits for today. So what I'm going to do is I'm going to do the volume of a right circular cone. So this is problem number 47 in the exercises. Let me clear the screen and state the problem. So number 47 is, so this is section 6.1, number 47. It's the volume of a right circular cone of height h, radius, and radius r. Okay, so let me draw a picture on how to do this problem. So there are various ways to set it up. I'm going to set the cone up like this. So what we have is I'm going to take a triangle, a right triangle, that's what it means to be a right circular cone, where the height is RH and the width is R, and then I'm going to rotate it around the y-axis. I could have set this up with the x-axis, but we might as well do the y-axis. Okay, so when we do that, so if this is a point, so first of all, what is let me give a formula for this line segment. It's y equals, the slope h over r times x. It goes to the origin, there's no intercept. So that's the what this line looks like. We could also solve for it in terms of x. X is r over h times y. We're going to need that actually, because we have to calculate the volume of the cross section generated by rotating it around the axis. So let me erase a little bit of this picture because I messed it up. Okay. So when we rotate that segment around the y-axis, you get you're going to get a circle. I'm going to draw the circle like this. And what's the radius of the circle? Well, the radius of the circle is the length of this segment. And what's the length of this segment? It's the x value. It's r over h times y. So the radius is r over h times y. So a of y is pi times r over h times y, quantity squared. Here r and h are constants. So this is pi r squared over h squared times y squared. So the volume is the integral. Now y is going from 0 to h, right? Of pi r squared over h squared times y squared dy. And we're integrating over y because we're rotating around the y-axis. And so that gives us, we can bring the constant out and integrate the y term, y cubed over 3, evaluated from 0 to h. And then we get pi r squared over h squared, h cubed over 3. There's some cancellation, you get 1/3 pi r squared h, and that is a well-known formula. You probably saw it back in high school. So that is the volume of a right circular cone. So you can see, like, the calculus approach to doing all of this really is very effective. You can calculate volumes of pretty standard looking solids in this way. And that's it for this lecture. Have a good day.